In this talk, I want to analyse the effects of the non-zero input currents to op-amps. Now, there are actually two types of input current that we need to worry about. One is the so-called bias current. It's a small amount of current that flows into the inputs of the op-amp no matter what the input voltages are. And the other is a current due to a finite input resistance of the op-amp. And you can model that latter current using this type of circuit model, with a Rin, an input resistance between the two inputs. Now, it turns out that if you build an op-amp with feedback, then that acts to increase the effective value of this type of input resistance, to the point where it rapidly becomes irrelevant in your circuit. However, the other type of input current, the bias currents, are a problem. Consider, for example, a non-inverting amplifier like this. We've seen this type of circuit before, but this time we'll take into account the effects of these input bias currents, these DC currents flowing into the inputs of the op-amp. We can no longer simply analyse RF and RB here in terms of a potential divider, because we've got some current being taken out of this tap here. We have to do something like this. Consider the voltage at this point here, the inverting input to the op-amp. I'll call it V-. At this node in the circuit, we can apply Kirchhoff's current law. The current flowing down through RF is V out minus V minus over RF, and that must be equal to the sum of the current going down through RB, V minus over RB, plus the current flowing into the input of the op-amp, IB, the bias current. Okay. That means that V out over RF is equal to V minus over RB plus V minus over RF plus IB. Now, since at the moment we're assuming the op-amp has an infinite gain, its action will be to try and get its two inputs to be the same voltage, V in equal to V minus. In that case, I have this expression. V out equals RF over RB plus RF over RF times V in plus IB times RF. Or in other words, V out equals 1 plus RF over RB times V in plus IB times RF. When IB equals 0, we just get that expression, which is the standard form of a non-inverting op-amp that we've seen before. But the effect of this bias current is now to introduce this offset voltage, this error in the output voltage equal to IB times RF. Now, in general, you don't know what the bias current of an op-amp is before you start to use it, but there is a clever circuit technique that you can use to eliminate the effect of this offset voltage. And that is to add another resistor into this circuit. We put the other resistor in here. So, the voltage on the non-inverting input of our op-amp is no longer equal to the input voltage in our amplifier, V in. Now what happens is that the voltage on the non-inverting input is actually V in minus IB times, I'll call it RC for compensation resistor. So I can substitute in for V in my expression here for the actual voltage, which is now on the non-inverting input of the op-amp, and get V out equals 1 plus RF over RB times V in minus IB RC plus IB times RF. Now what I would like is for this just to equal that. And I can do that if I choose the value of RC correctly. This is equal to 1 plus RF over RB times Vin minus IB times 1 plus RF over RB times RC plus IB times RF. Now, if I choose RC so that this term here is equal to this term here, then these two terms would cancel out. What I need, in other words, to get the output of my op-amp equal to the output in the case of an ideal op-amp is just to have this term equal and opposite to this term, which means 1 plus RF over RB times RC has got to equal RF. Solving this for RC gives me that RC equals RF times RB over RF plus RB, which you might notice is the same formula as we would get if we were trying to calculate the resistance of RF and RB in parallel. And that's not a coincidence. Conclusion: if I put an additional resistor there, RC, on my input, and select RC so that it's equal to the parallel combination of RF and RB, then my amplifier here behaves like a perfect op-amp. I have cancelled out the effect of the input bias current into my two inputs. You can do an exactly similar calculation for the case of an inverting op-amp. And if you do that, you'll find that you can eliminate the effect of the input bias currents by choosing a resistor between the non-inverting input and ground, which is equal to the parallel combination of Rin and RF. And if you put that resistor there, you'll find that the effects of the input bias currents into the op-amp cancel out, and the output is just equal to minus RF over Rin times Vin, as it would be for a perfect op-amp with no input currents. A problem with trying to do this in practice, however, is that the two input currents, the bias currents into the two inputs, are not exactly equal. Designers of op-amps try to get them as close as possible, but they can't get them perfect. And the difference between the two input bias currents is known as the input offset current. And it's a much harder thing to try and eliminate by adding extra resistors like this. To have a look at some typical values. For the op-amps that we've been using in the course this year, the LM358, bias current 10 nanoamps, offset current, that's the difference between the two bias currents, 0.5 nanoamps. It's 20 times smaller than the bias current, but it's not completely negligible, especially in the case where you're using very large resistors around the op-amp. And in fact, the bias currents and the offset currents in op-amps is one reason why you may choose not to use very large resistors in the input and feedback networks of your op-amp amplifier. You can get much better performance than the LM358. The TL071, which is a typical op-amp that we tend to use in labs quite a lot, and the MCP6002 are both CMOS op-amps. And that's a type of technology which gives you much, much lower input currents. Tends to give you larger offset voltages, but we'll talk more about that later. As is typical with engineering, there's always a trade-off. The 741 was one of the original op-amps, and I've just included it here to show how things have improved in the 40 or so years that people have been designing op-amps. That's all I want to say about the input currents. Next time, we'll have a look at the offset voltage.